Two races and in the most dominant season of Red Bull in Formula One history, helping to develop the car of Max Verstappen, developing front suspension, developing ride, developing kinematics, and doing basically my dream job. So today, this competition I was volunteering to give a little bit of this, to pass a little bit of the knowledge I've had during the years, which I've learned through failures, through reading books, through attending many other Formula student competitions, through my professional career. I've done a little bit of everything. I've been a tire modeling engineer. I've been a vehicle simulation engineer in a Formula 2, Formula 3 team. I've done passenger car consultancy for many different OEMs. Probably my biggest role so far has been as a vehicle dynamics and analysis engineer in Red Bull Racing. And currently, I'm in a transition between race performance engineer in Audi Formula 1 team, where I serve as a race performance engineer for Nico Hülkenberg. And currently, I'm transitioning to developing my own company in racetrack dynamics, where we do basically training, vehicle dynamics training, aerodynamics training, online and on-site courses, but also a consultancy project for different motorsport teams and passenger cars. So I really think that a successful Formula student season starts with planning. So the 8-9 months that you have between the end of the last competition and the beginning of the first happens really fast. So as soon as you can, sit down with your team, define your foundations. What do you really want to achieve? It's very, very obvious that not every team will have the same goals. Not every team will have the same objectives and performance targets. I think what is important is to set realistic targets, define the structure, responsibilities, identify the budget you will need to perform the activities, and go search it. So again, not every Formula student team is the same. Of course, large and structured teams will be much more specialized. There will be much more focus on pursuing engineering excellence. They will be pursuing higher technical solution, more technical solutions, and there will be more separation between the different roles and the different categories. Where small emerging teams will be required to have more cross-functional and interdisciplinary roles, and they will be required to have more flexibility and collaboration across the areas. Again, well-funded teams, they will have this ability to express all this knowledge, all this engineering excellence through innovative solutions. They will be able to design all the parts that they want. They will have bespoke solutions. They will have much more ability to pursue these sophisticated designs and budget-constrained teams. Here, the emphasis will be placed more on the creativity and how they manage to make competitive designs with the budget constraints that they have. Again, one thing that has been very concerning in past Formula student competitions is sometimes how know-how is lost across generations. Especially for experienced teams where a legacy has already been built, and there has been plenty of effort from past generations to build this, and I think it's current team members' responsibility to preserve it and just to go up. So again, experienced teams, at this point, they will be focused on refining the tools, on setting up the bar higher and higher. Obviously, developing teams at this point, they might not be looking at so much this level of sophistication. They will be looking at simple models, more fundamental engineering approaches. But I think what is the key principle here is that both set realistic targets, and they fight for their goal, whether it is completing the inspections or it is finishing on the podium at the end of the competition. Every goal is valid if it helps you to improve and to get better every week, every race. So one of the first things also in the design in the season should be to study the rules. It can be boring, very, very boring. It's not exciting. I really get that. I had to go through that as well in the past. But you can treat this as an opportunity to actively learn and find hidden areas of performance. We see it in Formula 1, but we also see it in Formula Student. Great teams have this thing in common where they are able to identify where are the loopholes where they can really get in and extract performance where others can't. Another important point will be learning the rules and the scoring system. The endurance is by far the most valuable point in the competition, which is 325 points. So that will require an emphasis on how you approach the distribution of the points you're trying to chase. Naturally, we're talking here about this is not a race. This is an engineering competition, and on the variable we're trying to optimize is the maximum amount of points. It's not lap time in the autocross, or it's not acceleration time. So usually reliability here delivers more points consistently than chasing a maximum performance objective. And we might be tempted to look at the more exciting or more challenging events like autocross, but if you think that autocross is only worth as much as a less exciting cost of manufacturing, maybe it can help us to prioritize the events in a different way. Because remember that what we're trying to maximize is points, not lap time at this point. So this, I believe it's important to understand your design priorities and to work from the beginning. So what we see here is it's a very complicated and complex vehicle dynamics model. It is completely multi-body. It had involved a fully dedicated team and manpower of thousands and thousands of hours, and this has a very high level of refinement. This here is also a vehicle model. So this is also not only a vehicle model, but a valid vehicle model. So the estimated workload of this piece of work is less than 20 hours, 2 to 20 hours, depending on the experience. There might be some people that will be able to code the thing in MATLAB or Python even in minutes. But essentially, I think you will agree with me that to take some fundamental decisions and some at least in the beginning, when we don't have all the information and we need to move fast, this is more than enough to justify our design directions. Once we get a model that we can use to interrogate and to find what is the solution that will help us to achieve the maximum number of points in the competition, we can start by interrogating it and finding what are the parameters where we need to focus more in order to extract points. Again, remember that we're not chasing lap time. We're not chasing downforce, although some teams are really excited about that. What we're chasing here really is score at the end of the event. So this will help you in your full decision-making process. What you need to do here is translate your lap time improvements in all the disciplines into actual points to take actionable direction. So please don't quote this plot. Don't use this this will be public. You will be able to download this presentation. Don't use this plot. This is only valid for a certain vehicle architecture. Every car will be different. Every track will be different. So your sensitivities are going to change. But just take this as an indication. Once you have run some simulations, you should be able to start answering some of these questions. You should be able to start answering whether your aerodynamic package is a good idea and if the downforce is worth that extra mass and inertia. You should be able to start answering whether you need to spend more time and energy into making a car lighter or into increasing downforce, especially as some teams are limited in manpower and resources. You should be able to start answering what is this desired battery size, how much weight you're willing to introduce to increase your score in the endurance, and where you will put the money for the better scoring at the end of the event. So all this will help you to take the first fundamental decisions of the design of your car. Once we get some of the basics resolved, for me, it all should start with the tire. I think for me and for most of the teams that were in the finals and that did well in the engineering design. So as you know, the tire is the only component that is connecting the truck with the car with the truck. Key component dominating vehicle performance, as you can see, as fast as you run some sensitivity studies in your lap time. It's one of the most sensitive parameters to not only to lap time, but to points in the competition. So you need to make the call first on which tire we want to be running, you want to be running in the car. And it can be a very lengthy task. We will need to navigate lots of data. I will go through that in a minute. But I believe there is merit in chasing this, especially for emerging teams. And this is where most of the resources should be aimed at to justify the rest of the engineering decisions that are cascaded after this for the vehicle dynamics development process. So how do we choose our tires? What you see here on the right, if you follow this QR code, you will also get it in the presentation. It will guide you to a very insightful video on how to navigate the amount of data that is available by the TTC. But generally speaking, there are some top teams. I'm not sure I've seen this in this week's competition. They used to work directly with tire suppliers to develop and specify bespoke tire characteristics that suit their vehicle from the early phases. But for the vast majority, and I think today for the totality of the teams, the tire choice is limited to the commercially available competition tires. So the Tire Test Consortium, it's an organization that provides an annual database of measured data that can be used for Formula Student tires. Essentially, they will buy all the tires on the market. They will send it to Calspan, which is one place in the USA, very far from here, where they will be testing them, and then all the data that they will make it publicly available. So you will pay a subscription, and you will be able to download all this data and to work with it. Then you will have your raw data. You will have a lot of points. You will have so many points that you will not know what to do with them if it's your first time doing this job. So that's why I hope this video can be insightful for this task. Then with the data that you have available at this point, it will be very difficult to decide which tire you want to run, which tire will be more useful to help you accomplish your goals. And so at this step, I think it's important to set up to use a choice matrix, give some weightings to your main performance targets. Please have a look at how I have deliberately hidden the parameter that I will consider for the different key areas. So it will be, for my case, it will be weight, transient response, sensitivities, any different sensitivities, peak performance, aggradation, temperature behavior. We've seen this as well. In the events, some teams with very good tires, but they struggle to make it work. They struggle to make it get in the right window. So this is something that can help you, again, to understand which is the tire that help you to perform better. So once we have candidates, or we have the tires that look more promising, that have scored more points, we should be in a position to start closing our window. And to finalize the decision, we will need to feed up a tire model to that. So what does it mean to fit your model to the data? I'm quite sure that we're familiar with a classic linear regression example. We have some scatter points, and we are just trying to infer what is the line that connects all of them with the minimum error. So in order to characterize a tire, we will need to do the same. We will need to get tires that are tested. We generate data, and then to this data, we will need to feed a model to that data, exactly the same way as we do with our simple linear regression example. So this is exactly the same thing. This is the same exercise, but now we don't have m and n that we need to find out in order to know how our equation works and to interrogate our model at any particular point. Now what we have is 100+ coefficients. So the task can become a bit more complex, but again, I think it's worth it. The exact set of equations that you choose for the tires is going to vary depending on the level of complexity, manpower, and energy you are willing to spend. The most common set of equations are the SME empirical tire model equations of Pasheshka, which are publicly available, unless some of the more complex and sophisticated physical tire models, which are developed by private companies. So these are equations that have been evolved during time, increasing the level of refinement and complexity and how much phenomena they can capture. So here we can see an example on how the first 5.2 and 6.0 equations don't have coefficients that model pressure effects, but as we go on and more sophisticated and newer versions, we start to account for those effects. Only now that we understand everything about the tire, we can start to think about making it work. So hardpoint definition is something that will need to happen very soon to pass this information to the chassis department, as the points that are connected to the chassis are the points that are which will be structurally more critical, where you want, the full point of the chassis is to get rigidity to provide the rigidity to ensure that the suspension works as it should. So kinematic points are maintained in space. So this is why this is the area probably that needs to be more critical and more carefully designed. So the sooner you got these points, the sooner they can work on iterating and providing the right package to accommodate it. So track and wheelbase should be clear from pre-design simulation and studies at this point. And we need to start by defining some package constraints which cannot be changed, or that from fundamental decisions we've made before, such as tire size, brakes, and uprights. So this will already define where we can place some of our points. Starting with the front view, one of our first tasks will be to understand where the front view instant center is going to be located. Depending on where we put the instant center, we'll have different degrees of compensation. We'll have different levels of camber compensations. When we put the instant center in the middle of the car, and this is one point that was also mentioned in the finals, when we put the instant center in the middle of the car, we'll have a pure camber compensation in roll, which means for every degree the car roll, the camber will be compensating every degree of it and will have no camber variation relative to our static camber in roll. However, this instant center in the middle of the car means that every time that there is heave or pure vertical motion between left and right wheels, synchronous motion, we will have the worst camber loss in heave. On the other side, if we push the instant center far past the opposite wheel, so our front virtual swimmer length at this point will be in the infinite, we will gain virtually no compensation in camber in roll, so that will force us to adopt another strategy and to probably raise roll stiffness or probably just deal with that. But we will have no camber loss in heave. So where do you put it? Really, it's going to be a compromise on your car philosophy. There is no right answer, but it will help us to start having a guess. So scrub at this point, as the side movement of the tire as the suspension goes up and down because of the instant center height above the ground or below the ground, will not be a problem at this point if it lies in a reasonable place. If your front is, it will not be a problem if your front IC is in a reasonable place. So just put it in a place that gives you your desired roll center. So many teams get lost in the roll center concept and spend so much time on one of the 100 things that need to be done that it is a fancy term. It is something that needs to be understood, but it's only one of the many things that we need to dial in, so move on. We don't need to master absolutely everything that we're doing because there is so much to do. If you are completely lost, it is the first time you approach this, there is no correct answer. Depends on your car philosophy. If you are able to justify where you've placed it in higher than that, that's totally fine, as long as there is a good justification process. But if you are completely lost and you are an emerging team, probably 30-40 minutes for the front is a reasonable number to start, and it gives you enough authority to play with your elastic elements to adjust the mechanical balance on the car when you need to make balance adjustments. Again, next will be in our steering geometry, kimping, scrub radius, and spindle length. They will all be affected by the outer ball joints. At this point, we should aim for a low kimping angle because it has some downsides, which will not always be possible because of the packaging constraints, and we will need to watch our spindle offset, especially with all-wheel drive vehicles, with all the EVs that are starting to have 4 engines for the 4 wheels. We will need to keep an eye on not only on the scrub radius, but at this point also on the spindle offset, because these will play a role in your torque steer, or how torque when you go on throttle will induce some level of understeer. It will higher kimping inclination angle will also induce a higher camber loss with steering, which depending on where you're sitting with the tire, but generally speaking, it will go in the direction of favoring understeer and helping and making that you lose front bite and front grip, which is something you want to avoid. And not only that, but kimping inclination angle, when it is combined with caster angle, it will have a jacking effect on diagonal, which makes your outboard tires on the front to be more loaded and more inefficient, and the front axle will be less inefficient and will also go in the direction of understeer. So these two phenomena of having a higher kimping angle will go and affect your balance. Next in the list is going side view. Caster angle induces some favorable camber gain with steering, which compensates the loss of the camber of the kimping. Again, here there is really no right value. Depends on your philosophy. How much camber angle does your wheel need to perform well? How much from bite do you want to gain mid corner to alter your balance? But this is a tool that, depending on the camber sensitivity to our car, can help to play with the balance of the car throughout the corner. Here, as opposed to when we were designing in the front view, we have more freedom to move the steering axis longitudinally, which means here we can meet both our targets of mechanical trail and caster angle. Tie rod location for steering should be such that the arc described but the outer tie rod hardpoint matches as closely as possible the arc movement imposed by the suspension elements of the upper and lower control arms. This distance to the steering axis, from the steering axis to this tie rod, will 10 Newton meters per degree is a relatively good number it's a reasonable number to target felt at the steering wheel. Next in the list will be anti-geometries. Again, the more your car is sensitive to ride height, the more anti-squat and anti-dive that you should be probably running, unless you have another design reason to not to do so. If you don't run aerodynamics in your car, your reasons at this point to use anti-dive are small. But even if you are using an aerodynamic package, don't abuse the antis because they also have side effects. They remove driver feedback, which is terrible, especially in Formula Student. The suspension becomes less compliant, and they limit the spring compression and wheel travel, which might be something you are using to create some desired balance characteristics, especially if you are inducing motion ratio with your anti-roll bar and your rocker. So kinematics are a good place to start, but nothing is rigid, as we know, and everything deforms under loads. At the bare minimum, the 4 things I will be looking at characterizing when designing the suspension will be these four compliance figures, which are brake camber and brake steer, and lateral steer and lateral compliance. So how much camber do I lose, and how much toe angle do I lose both under braking and under lateral acceleration? And one sentence that I've heard to death, and I've been repeated, is that compliance is the evil, is that something that needs to be minimized and reduced and whatnot. And I agree that if you don't have particular compliance strategy, you should aim at minimizing it, but it's not necessarily something bad, especially when you understand it, you calculate it, and you intentionally use it in your design. So if you don't have a reason to run compliance, do your mechanical design and suspension as efficient as possible. I think we don't need to go really into the weeds on what is an efficient design. I think a picture is worth 1,000 words. So we don't need to be pro-mechanical designers or even engineers probably at this point to see which one is the mechanical design that shows the best mechanical design practices. So it is okay to have some mild and intentional compliance. I'm not against that, but it's not okay to have excessive and non-compliance. Next in the list will be designing and speccing my springs. How stiff do I want my car to run? Major driver of performance and driver of the interaction between aerodynamics and vehicle dynamics. The task will depend on how aggressive your aerodynamic package is, how bumpy your track is going to be. In general, I think a good practice is to allow around 40% of your roll stiffness budget to your anti-roll bar. Again, the stiffer your anti-roll bar is, the more your independent suspension will no longer be independent, as forces will be transmitted between the left and the right. But then what we can use to figure out how stiff do we want to run the car, to find out our compromise between aero and ride, as I will approach it, if I don't have, if I have a limited amount of time and resources, without going much more complex stuff, we'll be designing a double track model to see and understand how stiffer suspension will enhance our response time of my system, and also a ride model that can help us to understand how this stiffer suspension will increase the CPL under different scenarios like heave and roll. Directionally, higher anti-roll bars will contribute to, as I said, high anti-roll bar contribution to roll stiffness will mean that we have a less independent suspension system. And don't forget that anti-roll bars are not only engaged in opposite wheel travel or roll, but they are also engaged in single wheel travel events, which is a single bump, for example, on the road. Roll stiffness philosophy will depend on the amount of aerodynamics you run in the car. If we have an increased roll stiffness, it will limit the amount of body roll, which is quite obvious, which is something positive, as it will also reduce the response time. This amount of body roll that is limited will help us to make, even if our sensitivity is low, it will still help us with our aerodynamic platform, and it will be a bad thing because it will degrade road compliance and ride in general. So the car will be bumping, will be jumping more, will be losing vertical load. And as I said, generally speaking, no aero will favor softer roll rates, and higher aero will favor stiffer rates. Not only because we will be risking bottoming with our front wing, but also because we are more concerned about our aerodynamic platform performing as flat as possible. Don't forget that we need to give plenty of adjustability to our car, especially since everything we are designing will be different when we test it in real life. We will have different conditions. There are so many uncertainties where the COG is really going to fall, what the aerodynamic balance is going to end up being at the end. So give plenty of margin to adjust the car. I really like a vehicle roll balance envelope like this, which gives me a map of all the configurations I have in my car to increase or reduce roll stiffness, and how that changes the roll moment distribution, which effectively will influence my mechanical balance or the ratio of lateral load transfer for the front axle relative to the total lateral load transfer. Next in the list will be to spec my dampers. If we have built a 7 degrees of model or ride model to specify our springs, that's something we have already. We don't need to readdress. That's something we can reuse. I believe that in Formula Student, your main goal at this point should be to reduce the contact patch load variation. There are a number of things that we can look at, but I believe this to be the single most dominant metric. Dampers will always need to match your spring, which means that your stiffer rates will mean more damping. So it's okay that you run your simulations and you end up coming with the dampers that give you the best ride response. But don't forget that every time you change your springs, every time you change your anti-roll bars, you are effectively changing the wheel rates, and the optimum damper settings will change. So remember that damping and rate will need to marry every time. Next in the list, when our car is done, is testing and validation. Test, test, and test. I think most of you will agree with me that there is a trend that shows that top-performing Formula Student teams consistently dedicate more time and resources into vehicle testing. In my opinion, this correlates with success for a number of reasons. First, because testing is a consequence of a strong project execution. And second, because it exposes the weakness of the design before we even hit the competition. It gives us time to react after failures, to adapt for the competition. And it also gives us plenty of margin to adjust everything that really came up as planned to really get the best of the package. Remember that it's okay that things don't go as planned. When we're designing, we're blind, really. But once we have the car on the track, we're testing, we're getting information. It is how we use this information when things are not as we expected, what matters, and what is useful to keep improving. So this flow path is essential in high-performance environments, and I think it's really useful to adopt it from the early steps. Use testing to validate your models and to understand what did not go right. And last but not least, it's compete and enjoy. You are probably among the most talented automotive and motorsport engineers. They are all reunited in the same place. It's okay if you feel challenged by people that, I mean, honestly, the level of knowledge every competition is impressive, so it can be quite overwhelming. But take this opportunity to see how they react and how they solve different engineering problems. They have the same engineering problem that you, so learn how they learn about their approaches. And again, these people that you are competing against and you are judged by, they worked, or they will work probably in the place that you will want to work as well at some point. They will go to motorsport environments, automotive, aerospace, technology companies, and even Formula 1. So don't forget to have fun, make friends, and create good memories, especially after all the hard work that came into designing your car. And to finalize, and to thank you for joining us today and for having us here in the competition, we want to share our FSAE toolkit. It's a toolkit that we have carefully designed for the competition. It contains obviously this presentation. You can access it by following the QR code or the link on the screen. It contains this presentation, our suspension kinematic simulation tool, which is completely web-based, free of charge, and ready to go in seconds. Within 5 seconds, you will be producing analysis and using it to make some decisions. Our lap time simulator tool, or the RD Lap Sim, which will be very, very soon available on 15th of August, where you can, again, in a web-based way, and again, completely free of charge forever, with no installation, with no licenses, just use it to validate your design, the design of your car, and to help you with your design directions. And finally, as well, our complete Wikipedia, or the books that I have read, that I have liked, and with a brief description of why I think that they were useful and what you can learn from them. So that was it. Here is the QR code to download that will take you to the website where you can access the presentation and all the free resources that have been discussed so far. Thank you for to all the teams for the dedication, their hard work, and the challenging engineering design sessions that we had. And I hope that all of you do very well. Thank you very much.